Oh, hi. Welcome. Hello. Hopefully we're doing all right today. Just kind of friendly reminder, we're not meeting in person today. So what we're doing instead is we're just going to do a little bit of a Calc 1 review. I don't think any of us miss these Zoom lessons all that much, and hopefully this YouTube lesson isn't too terrible. My plan for today is for us just to go over some of the things from Calc 1 that maybe we've forgotten, maybe we just need a little quick reminder as to how they work. I'll try to keep it relatively short, and we should be able to get through a lot of this pretty quickly. This is one of these things where, as we're going throughout the rest of the semester, if we do have questions, please let me know. We can explore some of these ideas a little bit more. I know that this isn't an ideal way for us to review. It would be a whole lot nicer if I could take some questions and interact with you guys, but I think that this will go quite a bit further trying to give a lesson on some review material today than introducing completely new stuff and expecting you to have it down ready for class tomorrow. So let's go ahead and let's actually begin. There is a lot of stuff that gets talked about right towards the top of Calc 1. For instance, you spend a little bit of time talking about limits, you spend some time talking about secant lines, you spend some time talking about limit definition of the derivative. All of that is great stuff. It's not going to be stuff that we really need a whole lot of in this class, especially at this point in time. So where I really want to start is I want to start with a review of our derivative rules. And there's a few of them. There's some of the function-specific derivative rules that I need us to know, or that we all need to know going into and throughout Calc 2. And there's some more of the bigger rules. So for instance, there's like the product rule and the quotient rule, the chain rule, the power rule. Those are the other rules that we need to know for Calc 2. So let me kind of just go through a quick list of the function rules that I expect you to know, and then we'll spend a little bit of time going into some of the bigger rules that I definitely want or expect you to know. So for instance, I do expect you to know how to take the derivative of like a polynomial. I'm not going to explicitly write down the power rule and the sum and difference rule and the constant multiple rule, but you should know how to take the derivative of a polynomial. You should know how to take the derivative of exponentials and logs. So in particular, the e to the x's or e to the u's and your natural log of x's or natural log of u's. So let me just write these as exponentials and logs. So in particular, e to the x's and the natural logs. In this class, we are going to do a little bit with like a number to the x power, or some problems involving logs with base other than e. When we get there, we'll quickly review those rules before going forward. So just for right now, I expect you to know the derivative of natural log and e. I will also say I expect you to know the derivatives of your basic trig functions. So you should be able to tell me that the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, the derivative of secant is secant tangent. Those are the ones that I'm going to expect you to know, kind of even off the top of my head. I don't even want to list out the derivative of cosecant and the derivative of cotangent because I'm afraid I might get them wrong. But I think if I thought about them for a minute, I could be able to rattle them off. But definitely sine, cosine, tangent, and secant. The other big ones that I'm going to expect you to know as far as functions are concerned are the derivatives of arcsine and arctangent. Those are going to be the two inverse trig functions that we use quite a bit throughout the semester. So let me actually state those. So arcsine satisfies the derivative of arcsine of x is going to be 1 divided by the square root of 1 minus x squared. Okay. And the other big function whose derivative I'm going to expect you to know in this inverse trig function category is going to be the derivative of arctangent. So here, the derivative of arctangent of x is going to be 1 divided by 1 plus x squared. So there we've got kind of the big functions that I expect you to know how to take the derivatives of. Polynomials, exponentials, logs, your basic trig functions, sine, cosine, tangent, secant, arcsine, and arctangent. Are there a couple more rules that you talk about in Calc 1 that I should expect you to know? Absolutely, like the derivative of arc cosine or the derivative of arc secant. But just being real, we're probably not going to use those all that often. So with this list of function derivatives, we should be good to go. All right, so now kind of continuing to build on this idea, we actually have a couple bigger rules. And these rules get introduced in all sorts of different orders. The way that I like to order the big rules, the big derivative rules, is I actually like to start with the chain rule. So the chain rule says that whenever you're taking the derivative of a composition of functions, so let's say you have some outer function, which is f, and then you have an inner function. Let's call this inner function u. Well, the derivative of the composition f of u is going to be equal to the derivative of the outer function. We leave the inner function alone, and then the last thing we do is we multiply by the derivative of the inner function. Right. Another way that the chain rule can be expressed is actually just using slightly different notation. So you might also see the chain rule expressed like this. The derivative of y with respect to x, you might also see written as the derivative of y with respect to some new variable u, I'll do u in a different color, times the derivative of u with respect to x. And notice that if you treat each of these differentials as if they are terms in a fraction, or factors of a fraction, what you will see is that the du's cancel and you're left with just the dy dx. But it is saying I'm taking the derivative of the outside function with respect to the inside function, and now I'm multiplying by the derivative of the inside function. So either of these representations of the chain rule give you the same exact thing. So let's go ahead and let's maybe just try an example involving the chain rule out. All right. So a fairly common chain rule problem might be something like this. Let's see if we can take the derivative. Let's keep it simple. Let's look at something like the natural log of, let's just do the natural log of a polynomial. So how about we have like a 3x to the 5th minus 9x squared. Are there ways that we could clean this up before taking the derivative now that I've written it out? Yeah, probably. But let's just go ahead and let's just dive straight into it just to do some of the calculus. Okay. So a few things worth inspecting here. We do have a composition of functions. We have this outer function, which we can think about as being the natural log. And because it is an outer function, I'll actually go ahead and I will just color code it using the same color code that I used up above. So now we have our outer function. And our inner function is going to be this 3x to the 5th minus 9x squared. So I'll go ahead and I'll color code that and make that orange. Okay. All right. So the first thing we need to think about is what is the derivative of natural log? Well, the derivative of the natural log is 1 over its argument. So whatever you're feeding into the natural log. So we'll start by just writing down the derivative of the natural log function. It's 1 over the argument. Well, the argument in this case is that 3x to the 5th minus 9x squared. So if we're keeping up with the color coding, this right here is the first part of our derivative of the outer function, and this is it now being composed with the inside function. So I'll keep the inside function orange. And then the last little bit of this is to multiply by the derivative of the inside function. Get the last little bit of orange in there. And the derivative of our inside function is just going to be the derivative of 3x to the 5th minus 9x squared. Well, the derivative of 3x to the 5th is going to be 15 x to the fourth, and the derivative of minus 9x squared is going to be minus 18x. Now, let's just go ahead and let's multiply this out. So we'll multiply across the numerators. That'll leave me with a 15 x to the fourth minus 18x all over 3x to the fifth minus 9x squared. And now looking at this, I see that all of the coefficients have a factor of 3 in them. I also see that we could factor out an x up in the numerator, and we could factor out an x squared in the denominator. So there is some cleaning up that we could do here, but as far as the calculus is concerned, we are finished with the calculus. So I'm just going to leave this problem here. If you would like to keep going with it, by all means, keep going with it, see if you can get it down to a very nice simplified form. I'm just going to leave it just like this. All right, so that is our quick little review of the chain rule. Next, we have the the product rule. So let's go ahead and let's spend a minute looking at the product rule. So what the product rule says is that if you're taking the derivative of a product of two functions, so let's pretend we have some function f times some function g. Notice that it is a product. We are multiplying two things together. Another word for multiplying two things together is taking their product. So what the product rule gives us is it gives us a rule from we're multiplying two expressions together, or two functions together. Now what does the product rule say? Well, the product rule says take the derivative of the first function and leave the second function alone. Then to that, you're going to add your first function times the derivative of your second function. So that is all that the product rule says. The product rule, fairly straightforward. So let's just think through an example with the product rule. So here might be a good example of a product rule. Maybe we'll combine a little chain rule in it also. Let's take the derivative of something that looks like x times, how about a sine of 4x. This seems reasonable. Seems like a good example, right? So again, just to keep up with the color coding, I don't think it's a bad idea to do the color coding, especially since I have the technology to do it. So let's go through and let's kind of color code each of our two functions, right? So I have my first function, just x, color coded red, and I have my second function, sine of 4x, color coded in pink. What the product rule says is that we're going to start off with the derivative of the first function. Well, here, the derivative of x is just 1. And that's going to be multiplied by the second function just the way it's presented. So we'll have a 1 times a sine of 4x. The next bit in the product rule says we have to put down a plus sign. Okay, that's reasonable. Then we're going to leave the first function just as it's presented, and we're going to take the derivative of the second function. So here we're going to take the derivative of sine of 4x. Well, here we do have to use the chain rule because we have a composition of functions. We have sine, and inside sine, we're putting a 4x. So the derivative of the outside function is the derivative of sine is positive cosine. Chain rule says leave the argument the same. In this case, the argument is the angle 4x. And then multiply by the derivative of that argument, or the derivative of the inside, which in this case is the derivative of 4x, which is just 4. So can we clean this up a little bit? I think we can, and I don't think it'll be too much work. So 1 times sine of 4x is just going to be a sine of 4x. The next little bit, just to make it a little bit more aesthetically pleasing, let's put the 4 out front, and we'll be left with 4x cosine of 4x. So that right there is our product rule. Next, let's go ahead and let's play around with our quotient rule. So this is going to be probably the last of our big derivative rules. So what does the quotient rule say? Well, it's kind of an extension of the product rule. So the product rule told us how to take the derivative of a product. The quotient rule is just a fancy rule that tells us how to take the derivative of a quotient. So what is a quotient? Well, it's just a fraction. So let's say we have some function f, and that function is being divided by some other function g. So say we have f divided by g, and we want to take the derivative of f divided by g. Well, the quotient rule says that this is going to be equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the original denominator squared. So there we have our quotient rule. Let's go ahead and let's just think through an example using the quotient rule. All right, so let's dream something up. How about we used polynomials, we used a sine. Let's do something maybe like how about we do a tangent? Let's keep it simple. Let's just do a tangent of x divided by, how about we do an e to the x squared? This looks pretty good. All right. So again, just to keep up with the color coding, we can color code our numerator. Think about that as a function f. We can color code our entire denominator, and we can think about this as some function g. So now we just need to put all of the right pieces in all of the right places, and we'll have our derivative. So what does the quotient rule start off with? Well, it just starts off with g. It just starts off with the denominator. So I am just going to write the denominator exactly as it's presented, e to the x squared. And what does that get multiplied by? Well, the derivative of the numerator. We know that the derivative of tangent, or we should know, the derivative of tangent is secant squared. And because there's not a composition here, we don't need to worry about a chain rule. So the first thing we have is the denominator times the derivative of the numerator is this e to the x squared times secant squared of x. Next thing the quotient rule tells us to write down is a minus sign. And now what are we subtracting? Well, we're subtracting the numerator, which in this case is just tangent of x, times the derivative of the denominator. Well, here we have this e to the x squared. So here we do have a composition of functions, so we have to use the chain rule. So the derivative of e to the x squared is going to be e to the x squared times the derivative of x squared, which is 2x. And that right there is our chain rule. So there's our numerator from the quotient rule. The last little bit that we need is we just have to square the denominator. So our denominator was e to the x squared. And we can go ahead and we can square that denominator. Now again, looking at this, there are a few things we can factor, there are a few things we can simplify, but as far as the calculus is concerned, at this point, we are finished with the calculus, so I'll leave it up to you to take this a few steps further if you would like. Now, that right there kind of summarizes a lot of the derivative rules that I expect you to know from Calc 1 going into Calc 2. Let's also spend maybe just a brief moment talking about some of the integration rules that I'm going to expect you to know going from Calc 1 into Calc 2. I'm going to give myself a few more blank pages here, so forgive me for adding these now. So integration rules. Here's where these become a little bit more interesting or require us to think maybe a little bit harder. And I don't think it's necessarily that the rules themselves are harder. It's just there's usually a little bit more work that has to go into applying the rule. So for instance, one big rule that you have for integration is something called the power rule. Which is the exact opposite of the power rule for differentiation. But it might be presented to you in this type of a form. So you might be asked to integrate u to some power n with respect to u. And as long as n is not equal to -1, this is going to be equal to u to the n plus 1 divided by n plus 1 plus some constant integration c. So let's actually go ahead and let's look at an example where we're integrating something of this form. So here we might have something that looks like an x times x squared plus 7 to the 9th power dx. Okay, so this right here does not necessarily look exactly as if it is in this form right here. It does not look like we are just integrating some u to the n du. However, it is in this form, but this is where integration ends up becoming a little bit trickier. So in order to get this expression to be in that form, we have to perform something that we call a u substitution, or we can also think about it as a change of variables. And the way that this works is I'm going to focus on the bit of my integrand, which is raised to a power, in this case the x squared plus 7. And I'm going to try to proceed through this problem by replacing this x squared plus 7 with u. So if u is this x squared plus 7, that means that the derivative of u with respect to x is going to be 2x. However, here's where I'm going to do a little bit of technology magic. I want to think about this dx here as if it were its own little expression, its own little factor that I could multiply both sides of this equation by. And this right here now actually gives me something to rewrite my differential in the original integral in terms of du. Right? So I'm actually going to grab this guy here. I'm going to color him, let's go pink. And I'm also going to color this x dx pink. And I'll show you why I want to do this in just a second. Right? So notice what we have in the original integral. I have a dx, and I have an x. So I can actually replace this x times this dx with a du over 2. So go ahead and watch this. I'm going to take both sides of this equation down here and just divide both sides of this equation by 2. So let me clean this up just a little bit. And I'm going to give this guy a little bit of color. Let's make him yellow. Okay, so now let's go back up to the original problem. Right? So it's still an integral, so the integral still has to come along for the ride. We've still got some stuff that's going to be raised to the 9th power. But let's go ahead and let's fill in everything else. So this x squared plus 7, right now I'm just calling x squared plus 7 u. So I'm going to replace the x squared plus 7 with a u. Now what else is there? Well, there's also this x dx. Well, I'm going to replace x dx with du divided by 2. I'm going to write the du to the right of my integral symbol, and I'm going to write the over 2 out in front of my integral as a 1/2. Right? Now, look at what we have. Now we have an integral of the form, the integral of u raised to a power with respect to u, exactly as is presented in the power rule for integration. So now we can actually just go ahead and we can follow along, and we can just integrate this. So this half is a constant multiple, just comes along for the ride. If we integrate u, well, u comes along for the ride. We add 1 to the exponent, so if I add 1 to 9, that leaves me with a 10. I also divide by the new exponent, so I'm going to also divide by 10. And now, since I'm doing an indefinite integral, I need to include my constant of integration plus c. Now, we can go ahead and we can clean this up just a little bit. So let's see what else we can do. Well, I have this 1 times u to the 10th. That's just going to be a u to the 10th. But what is a u? Well, remember, u was the first substitution that we made right here. So the very first thing we wrote down was let u be this x squared plus 7. So I'm actually going to go ahead and I'm going to replace u with x squared plus 7. Now remember that x squared plus 7 is still raised to the 10th power, and it's being divided by 2 times 10, which is 20. And then we're asked to add this constant of integration. Now we're asked to add a plus c. So that right there is how we evaluate the integral of x times x squared plus 7 to the 9th with respect to x. We actually go through the process of a u substitution, we rewrite the integral, and we evaluate the integral. All right. Now, there are a few more integration rules that we need to know or to be proficient in to be successful in Calc 2. And a lot of these are things that we can review a little bit in class. But one of the big tricks or one of the big types of rules that you probably need to know or to have down as we go forward is a kind of a simple case of what we just talked about here. All right. So something that you may have noticed even me doing already in class is if we have something that looks like the integral of, let's say, e to the 8x dx. This right here is a good integral to evaluate using u substitution. It's one of these problems that in a typical Calc 1 class, I will go through the u substitution each and every time. However, now that we're creeping into Calc 2, I'll go through these types of integrals a little bit more quickly. So in class, you might see me look at something like this and just write down, oh, the integral of e to the 8x is going to be e to the 8x divided by 8 plus c. And the reason for this is because I'm quickly doing a u substitution in my head. I'm actually thinking about how I would undo the chain rule from differentiation. But let's think about what the u substitution would look like here. Right? So the u substitution for this problem would actually go something like this. I would see that I have this e to the 8x, and I know how to integrate e to the u. So going into this problem, I know that the integral of e to the u with respect to u is going to be e to the u plus c. So that's all that I know going into this. So my approach is to just let u be the exponent. And I need to perform a similar trick to this last example. So I'm going to take the derivative of both sides. So du is just going to be 8 dx. I don't have an 8 dx, so I can actually just divide both sides by 8 and bring the 8 over here. Oop. So now I have dx is du over 8. So I'm going to replace this dx here with du divided by 8. So now what are we left with? Well, now we're still trying to evaluate this integral of e to the 8x. But I'm replacing the 8x with a u. And I'm replacing the dx with a du divided by 8. So I will replace the dx with du, and the divided by 8 I will write out in front of the integral symbol as 1/8. So now this 1/8 comes along for the ride. I know that the antiderivative of e to the u with respect to u is e to the u. And now I need to include my constant of integration plus c. So finally, just to bring all of this back together, I need to recognize that this u here is this 8x up here. So again, this u right here, sorry, started circling the wrong u. This u right here is this 8x from up here. So we're going to replace u with 8x. Instead of writing 1/8 out front, I'm just going to divide e to the 8x by 8 and continue to include my constant of integration. So there we actually have a quick little integration involving a u substitution that we can do in our head. And now we're actually at a point where we could do a lot of these pretty quickly in our head. So for instance, say we were in the middle of working through a problem and we saw something that looked like the integral of, let's say, cosine of 7x plus 3 dx. This is something that we should be able to look at and say, oh, the antiderivative of cosine of 7x plus 3 is going to be sine of 7x plus 3 divided by 7 plus c. I didn't give myself enough room for the plus c, so let me shrink this down a little bit. And we'll include the plus c. Or another example where we might see something like this might be if we were in the middle of integrating, let's say, a secant squared of 8x. We should be able to identify that this is going to be a tangent of 8x divided by 8 plus c. Now, if you aren't able to see where either of those came from, I highly encourage you to think through the entire u substitution and make full, complete sense of both of those two integrals that I just wrote down. So with that, I do think I'm going to go ahead and leave this here for today. I think that this is a pretty good review of a lot of the rules that you need to know from Calc 1 in order to be successful in Calc 2. As more things come up, or if I do find anywhere that we do need to spend some time reviewing, we can and will review those topics in class. So with that, have an excellent remainder of your day, and I'll catch you tomorrow. Thank you.